Okay, for the second part of this video, we're gonna finish this final exam. It's just actually more advanced topics in microeconomics, so bear with me. Here's a condition of on-choice correspondences called alpha 0. If x is in the choice correspondence and y is in the alternative set, and x is different to y, then x is in the choice correspondence defined by the set xy. And does alpha imply alpha 0? So remember, this alpha is they're talking about right here. It's actually sense alpha. Recall. Let's recall this. Recall sense alpha condition. This means if x in the choice correspondence and x in a subset of A, then it must hold that x is in the choice correspondence over B. Okay, and let's show A. So suppose C satisfies alpha and fix A. Okay, sorry about that. That's A. To show, what we want to show here is that alpha implies alpha 0. This is actually equivalent to showing that x is in C over the set xy. Okay, so let's pick any x in the choice correspondence and y in A. Okay, and such that x is different to y. Okay, since this is a direct result of choice correspondences of choice theory, that the choice correspondence must be a subset of the alternative set. And this means by this condition right here, the red one, and yeah, so this must hold that x is also a member of A, right? Yeah, and therefore x is in sorry about that. Therefore the set xy is a subset of A, right? So we are saying that we are saying that C satisfies alpha, right? We know this because we're supposing it. We're using it to prove that alpha implies alpha 0. This actually follows trivially from here. So given x is in CA, right, it is obvious that from this condition x is in xy, right? And so given that x is in xy and y is a subset of A, right? So and x is a subset of xy, obviously, and that's it's a member of the set xy, and that's a subset of A. Then by alpha, x is a member of the choice correspondence over xy. And this actually proves what we wanted to show. And to show B, we have to do a little bit of more thinking. So we have that alpha 0 implies alpha. Well, if x is a member of CA, let's recall alpha, okay, y is a member of A, then x is different to y, then x is in the choice correspondence over the set xy. right? And we want to show that alpha 0 implies alpha. Okay, and well, again, C is the choice correspondence over A is a subset of A. Then X is also in A. We're using the same condition we used in the previous proof, and therefore X and Y is a member of A, right? But what if we define A as X, Y, W, Z? Then the following choice correspondence satisfies alpha 0, but fails at alpha, right? So we know that we can do Wx over Wx, Wy over Wy, shalala, shalala, whatever, and Yc over Yc, right? This looks like 4, I'm sorry, Yc. This actually satisfies alpha 0, right? But what happens if we have a choice correspondence over X, and this is not defined, right? This is actually not implying me that this will hold. I cannot assure that this will hold, and therefore alpha 0 does not satisfy alpha. Yeah, we have a failure at alpha. We have that X is in CA and X different than Y in both in XY subset of A, but this is not implying me that X is in the choice correspondence over XY. Alright, so you have to be careful in that. This is not implying. Therefore, I can construct a set A which does not, which satisfy, let's say it this way, where C satisfies alpha 0 but fails at alpha. Okay, so that's that, and we'll go to the last question, and this is actually a pretty easy one. So we have let X be a finite set of alternatives for any set of probabilities on X, where P and U are lotteries, and we will show that we want to prove that this preference relation has a expected utility representation. So by the von Neumann theorem, this satisfies, this looks like a G, I'm sorry, satisfies independence. Right? So this is pretty straightforward. Let's say that let U of X equal, let V of X equals U of X if X is not in S, and 0 if X is in S, right? And then we have to recall what is independence. We have two lotteries over the preference relation Q if and only if alpha P plus 1 minus alpha R is weakly preferred or preferred to alpha Q plus 1 minus alpha R, right? So we want to show this. So we have P weakly preferred to Q if and only if what? Well, VP. Actually, this definition we're gonna use this one right here. We're gonna plug it right here. It's greater or equal than the expected utility of Q. So this is if and only if, and X is not in S. Px, then we have to use Ux plus 1 over the cardinality of S. X is in S. Ux greater or equal than X is not in S. Q of X, U of X plus the cardinality of X in S, U of X, right? These terms right here are actually numbers, so they can be canceled out. So this goes with this one. This goes with this one, and we have that X is not in S. Px U of X greater or equal than X is not in S. Q of X U of X, right? And as X is not in S, remember how we defined the V. In fact, we can actually say it's lowercase v. Okay, so we'll use it right here. So this is if and only if X is in X, right? Px Vx greater or equal than X in X, Q X Vx, right? And we have finished here. Hence, this preference admits E expected utility preference with the underlying utility V over the set of alternatives X, and therefore this preference satisfies independence by the von Neumann theorem. And yep, we finished the tests right here, and well, I hope you understood everything. I think it's pretty straightforward. It's a test you can actually finish in less than an hour. So yeah, if you have any doubts, please leave it in the comments and I'll try to answer them. Thank you for everything, and see you next time.